Okay, we should be sharing to YouTube and also screen sharing. And it is a couple minutes past, so I'll go ahead and get started. So today for the discussion, we're mostly going to be going over some problems to help you review for your quiz. And then there also are some problems from quiz 2 that we're going to go over. We might not get to all of them, but if we don't, they will be addressed next week. Okay. So our very first problem is an element-wise proof. We're given A and B are sets and use the universal set. And then we need to give an element-wise proof for the following. So we have that A and A intersect B equals A, and we want to prove that A complement union with B is the universal set. So I will give you all just a couple minutes to work on this one. Let's see. Okay. So 2 minutes, go ahead. And then also just keep in mind while you're working on it, it might be good to, this is what we're given, right? We are given that A intersect with B equals A. So it might be good to put a Venn diagram down so that you have a good understanding of what this is telling us, because that's going to be really important to the proof. All right, that's 2 minutes. So I'm just going to hurry and draw the Venn diagram that I was talking about. So we have, this is just the whole universal set. And if A intersect with B is just A, then that means we have B, and A has to be within B. It's a subset of B in order for this to be true. Okay, so what is usually the method that we want to use when we're trying to show set equality? So if we're trying to show that A complement union with B is equal to the universal set, what are the two different cases that we have to prove?
Do we have to show that they're both subsets of each other?
Yeah, exactly. So let's start with our first case, which is that we want to show that A complement union with B is a subset of the universal set. All right, so we want to do an element-wise proof. So let's say that X is in A complement union with B. All right, this one's kind of tricky because it doesn't seem super obvious. But this actually, by definition of the universal set, already means that X is in the universal set. And the reason why is that if we have X is in A complement union with B, then let's remind ourselves, we've got this Venn diagram up here. This is everything that's outside of A. So let's just color it all in. And then the other option is that it's in B. So if it's in B, like if it includes something that's in B, then we are also including everything that's in A, since A is a subset. So this is actually including, let's see, X is in this set just implies that X is in the universal set because everything is covered. All right, and since this implication is true, then A complement union with B is a subset of the universal set. All right, so then let's move on to our second case, which is that we want to show that the universal set is a subset of A complement union with B. So once again, we're going to let X be in the first set, which is the universal set. All right, and we have, by definition of complement, we can actually split this up into two cases. So does anybody know what those two cases are?
Would it be X is in A or X is in B?
Not quite, and the reason why is that we don't necessarily, A and B aren't complements of each other, right? So they don't necessarily take up all of the universal set. But so we do want to include A. What is something else that we could include, like two cases of A where it would include all of the universal set? All right, so let's do our first one, which is that X is in A. And 2.2, what set does X need to be in that without a doubt it will fill up the rest of the universe?
A complement.
Yes, X is in A complement. So let's start with if X is in A, and we're trying to show that it is in the set A complement union with B. So we're given up here that A is equivalent to A intersect with B. So that means that X is in A. X is in A implies that X is in A intersect B. And that's by definition of set equality. So if X is in A intersect with B, then we know that X is in B and X is in A by the definition of intersection. And if X is in B, then X is in anything union with B, right? And that's by definition of the union of sets. So then we can say that X is in A complement union B. So that one's all taken care of. All right, and we're going to use a similar method, a little bit more simple with our 2.2 case, which is that if X is in a complement, then what else is in? What else is X in? And we're going to use the definition of union, if that's
So if it's in complement A, it's also like in B because we have like union with B.
Yep. By definition of union. And that's using this same property that we had over here. All right. So in both of these cases of 2, we have that X is in the universal set implies that X is in A complement union B. So the universal set has to be a subset of A complement union with B. And then what is the conclusion going to be for the entire thing? All right, so remember that we started off with 2 cases, and whenever we finish up these 2 cases, it's good to like combine them in our conclusion statement. And so in this case, we would want to say, since a complement union B is a subset of the universal set, and the universal set is a subset of a complement union with B, then they have to be equivalent, which is from the definition of set equality. All right, are there any questions on that? Okay, awesome. We will move on. So now we have a proof by contradiction. We want to prove that the set 2k plus 1 such that k is in the set of natural numbers, and 4k such that k is in the set of natural numbers is the empty set. And we want to use a proof by contradiction for this one. So I'm going to go ahead and set the timer for 2 minutes again and go ahead and work on it. All right, that's 2 minutes. So the first thing that we need to figure out is what a contradiction would be in this case. So does anyone want to say what they used for their contradiction?
I said assume there's a natural number x where, or not a number x, but assume there's a situation where 2k plus 1 equals 4m.
Okay. That is correct. I'm going to go back just a couple more steps so that we have a basis for saying that, which is, so a contradiction would be that here, and I'm just going to call these sets A and B. A contradiction is that A intersect with B is non-empty. And if it's not empty, that means that there's at least one element. So let's let X be in the intersection of A and B. And then by definition of intersection, X is in A and X is in B. And that means that X equals 2k plus 1 and X equals 4m. So by substitution, that's where we can say that 2k plus 1 equals 4m. All right, so now we've got a setup here, and there are a few different ways to solve this. This is one of those proofs that has a lot of different options. So I'm going to show probably the less obvious one that I would assume less of you attempted, just because there is one that's a little bit easier to come to when you're looking at it. So if we have 2k plus 1 equals 4m, we can do some rearranging here to get 1 equals 4m minus 2k. Just subtracted 2k from both sides. And we can factor here, which gives us 2 times 2m minus k. And if we divide by 2 on both sides, we get 1/2 equals 2m minus k. Oh, and I also forgot to specify up here. M and k are in the set of natural numbers. Remember that the set of natural numbers is a subset of the set of integers, so we can still use closure under integers, which means that we have here a rational number, and we have on this side an integer, where 2m minus k equals c, and c is in the set of natural numbers by closure. So this is a contradiction because an integer can't be represented as 1/2. So that means by contradiction, A intersect with B has to be the empty set. All right, are there any questions on that one? Okay, awesome. And remember, oh, I forgot to say, if you did it another method, if you showed that one side is odd and one side is even, that's also good. Just make sure that you have that you specify what set your variables are in, and that you, at least in a formal proof, I know I didn't specify this on here, that you have some way to explain why the set of natural numbers is a subset of integers. Okay. All right, now we've got a power set problem. So A and B are sets, and we want to prove that the power set of A intersect with the power set of B is equivalent.
Sorry, I had one little question.
Okay.
If you go to the previous slide, you said C has to be in n by closure, but can't we only guarantee that C can be in the set of integers by closure under subtract? Because natural numbers aren't closed under subtraction, right?
That's right. Sorry about that. So that should be, thank you for catching that for me. C is in the set of integers. All right. Sorry about that confusion. Any other questions on that one? All right. Okay, so we're proving that the power set of A intersect with the power set of B is equal to the power set of A intersect with B. So I will let you all work on this for a couple minutes as well, and then we'll come back together. All right, so let's come back together. Again, we have a set equality problem. So what does that tell us about our cases? All right, so remember, if we're proving set equality, we want to show that both sides of the equal sign are subsets of each other. So for our first case, we're going to want to show that the power set of A intersect with the power set of B is a subset of the power set of A intersect with B. We're going to do an element-wise proof for this, but keep in mind that the elements of a power set are not elements, but they're actually sets. So for our element, we can let C be a set that is in the power set of A and the power set of B. And so we establish that C is in this intersection. So what does that mean about C?
C is in the power set of A and in the power set of B.
Right. So by definition of intersection, C is in the power set of A and C is in the power set of B. All right, so now we want to figure out something about C's relationship to the set A and C's relationship to the set B. So let's see. Let's say C is in the set A. What's wrong with that?
C is a set, not an element.
Exactly. So what is a better way to describe this relationship?
C is a subset of A.
Yeah. So C is a subset of A. I'm just going to move this up a little bit. And that also means that C is a subset of B. All right, so if C is in C is a subset of both of these sets, then that means C is in the subset of the intersection of these sets. And that's by definition of intersection again. All right, and if C is in the intersection, or if C is a subset of the intersection of these sets, what does that tell us?
That C will be in the power set of A intersect B.
Yep. So C is in the set that is the power set of A intersect with B. So we proved the first case, awesome. The second case is going to be really, really similar. It's just kind of going to be reversed. So we're wanting to show that the power set of A intersect with B is a subset of the power set of A intersected with the power set of B. So once again, we're going to let C be in the set that is the power set of A intersect with B. And we can already jump to showing the subset steps. So we can say that C is a subset of A intersect with B. And forgot to specify this early, but that's by definition of a power set. All right, now we've got that C is a subset of A intersect with B. So C is also a subset of A and C is a subset of B by definition of intersection. And now we can go to the power set. So C is in the power set of A, and C is in the power set of B. And here's our last step. What does this tell us?
C is in the power set of, or power set A intersection power set B.
Yep, therefore C is in power set of A, intersect with the power set of B. All right, and then again, we have our final conclusion statement. So we can say, since this is gonna be a long conclusion, since the power set of A intersect with the power set of B is a subset of the power set of A intersect with B, and the power set of A intersect with B is a subset of the power set of A intersect with the power set of B. I'm just going to move this all down because I don't have enough space. Then, by definition of set equality, the power set of A intersect with the power set of B is equal to the power set of A intersect with B. And we can finish that proof. All right, so let me zoom out a little bit so we can see it all together. Does anyone have any questions on this? All right, we'll move on.
Question.
Oh, okay.
So if something is a subset of another set, is it always going to be an element in the power set of that set?
Let's see. Sorry, repeat the question just so I can double check I understand.
Yeah, so if C is a subset of A, C will always be an element of the power set of A.
C is a subset of A. Yes, because the power set includes every single possible subset. That's the definition of the power set. So anything that any possible subset of A is going to be in the power set. So we can make that jump always.
Okay, yeah, thank you.
Mhm.
So I have another question about that sort of in reverse.
Okay.
So I guess I'm just confused at how that works in reverse, because like when you say C is an element in the power set of A intersect B, how do you know that C is automatically a subset of A intersect B? Like the second and third lines in the part 2 of this proof.
Part second and third, right? Okay. So if C is an element of the power set, then C is a subset. Okay, would it be, is it just the intersection that's confusing you, or is it this this top step as well, where we go from C is an element of the power set of A to C is a subset of A?
Wait, sorry, let me look at the top part. Say that top part again.
Yeah, so we say that C is an element of the power set of A, so then C is a subset of A.
Oh yeah, that's a simpler way to look at it. That is also confusing me.
Okay, all right, so let's just say, I'm just gonna do a quick little example of the power set. So let's say that A is the set of 1, 2, and 3. Then let's just list out everything that's in the power set of A. So you can shout it out or put them in the chat, just whatever I hear, I will put down.
So a set with 1, a set with 2, a set with 3.
Empty set.
Okay. Yeah, and I'm gonna actually move the empty set up to the top. Okay,
and then like a set with 1, 2, a set with 2, 3, and a set with 1, 3.
All right, and there's one more.
The entire set, right? 1, 2, and 3.
Okay, so let's just blindly pick one of these sets. 1, 2. So let's see. Would you agree that 1, 2 is a subset of 1, 2, and 3?
Yeah.
All right.
I see how this works now.
Okay, yeah. So that's just by the properties of how we construct a power set, we are including every possible subset. So any element that's in the power set is going to end up being a subset. And
right.
every subset that we could possibly make of A is going to be in the power set.
Okay. Okay, thank you. That makes sense.
Yeah, no problem. All right, any other confusion on this? I know this one's kind of tricky. All right, let's go on. We are going to use the properties of Boolean algebra to do this problem. And we want to show that A plus B times B plus C is equivalent to AC plus B. But the little trick here is that we're given the Boolean algebra properties instead of, let's see, we're given the propositional logic properties instead of the Boolean algebra, so we need to kind of like convert them in your head. So I'm just gonna let you work on this one for 1 minute. And just remember that a caret, I think that's what it's called, I'm not sure. The and symbol for Boolean algebra or for propositional logic is going to be equivalent to multiplication in Boolean algebra. And the or symbol is equivalent to the addition symbol. So timer is going for 1 minute. Go ahead and work on this. Okay, that's 1 minute. So let's get started on this one. And we're trying to show that A plus B times B plus C is eventually going to equal AC plus B. Now, we were talking about this, me and the other TAs were trying to figure out because there are a couple ways to do this problem. One of them is a little bit more complicated and one of them is a little bit more simple. So I'm going to show what I went to when I first looked at this problem, but if anyone tried something else, we can also go over that because there are multiple options. So what I looked at when I first saw this problem is that it looks really close to the right side of our distributive property. We've got the or sign or the plus sign in the parentheses, and we've got the multiplication or the add sign in between them. But what do we have to do first before we can use that property?
Commutative?
So we need to switch B plus A over B plus C, and that's using the commutative property. All right, and now we can use the distributive property. So what would that turn this into?
I have a question. Do we really need to like do the commutative property before as like to explain?
So it seems the commutative property seems really trivial a lot of the time, but remember that commutative property, just we're so used to it with integers that it seems like automatic, but with things like let's say in linear algebra, when we have oh goodness, why can I not remember the name of these that have all the numbers in them? Anybody want to help me out here?
Matrix?
Is it a matrix?
Matrix, yes. Oh my gosh, that was like the worst brain fart ever. Matrices are not actually, they don't have a commutative property. If you multiply B times A, it is not the same as A times B. So when we're dealing with things that are not integers, it's good to specify because the commutative property isn't always applicable. Does that make sense?
Yeah, that makes a lot of sense. Thank you.
All right, so let's see. We're moving on to applying the distributive property. So we're using this right-hand side of the property, and we want to move it over to the left-hand side. So what is the equivalent in Boolean algebra? And we have, so in this case, we're saying instead of P or Q, we have B plus A. And instead of P or R, we have B plus C. And in between, we have a multiplication. So what does that mean for the left-hand side? All right, so if we're saying that P is equivalent to like B in this case, then we would have B and then switch the or sign to an add sign. And then we have Q, which we're saying is A, and then times instead of and C. Does that make sense how we converted that? All right, so because of the way that Boolean algebra is written, we can also just say, oh, and I should put distributive. We can say that this is B plus AC. That's equivalent. We don't need to use a property. It's just how it's written. So then we're really close to this last step. What is the last thing that we need to do?
Commutative.
Commutative. All right, and there's the answer. We only had to use 3 properties. There is a different way to find the solution. Did anybody else use that? The alternative method. All right, if nobody used it, are you interested in seeing it?
Yeah, let's see it.
Okay, so we can also, let's see, A plus B times B plus C. Let's see. So we can use the distributive property to kind of split this up. Let's see. Yeah. So instead of using the reverse of the distributive property, we can just use a slightly more complex version of the distributive property, and we can write it as A plus B times B, and then add that to A plus B times C. And that's using the distributive property. All right. What is, let's see. There is a property here that we can use, but we're going to have to rearrange a little bit. Does anyone want to say what their next step would be? So we're going to need to use the commutative, but what is going to come after that? What's our goal? You're all very quiet today. All right, so let's use the commutative property. We want to eventually use absorption because we can see these two b's next to each other. We can use the absorption property, but in order to make it look more like our absorption, or I guess it's, yes, it is this one. In order to make it look more like that, we just need to rearrange and say b times b plus a plus c times a plus b. And that is with the commutative. So now we can use absorption and say that this is equal to, or let's see. Yes, this is equal to b. And then we have plus c times a plus b. And that was with absorption. All right, now what do we want to use for this term right here?
Absorption again.
So remember that for absorption, we need to have these two first variables need to be the same.
Of course, that's right.
Oh, would you use the distributive property there?
Yes. So now we can see this is equal to b plus c times a plus c times b, which is from the distributive property. All right, we're getting there. We're going to want to use absorption again, but we need to use commutative one more time, or not one more time. We're going to need it again. We use commutative a lot. So this is equal to b times c plus a times c. And we're just switching that one because we know that we're eventually going to want ac plus b. So this is commutative. And now we can use the second version of the absorption property. And that gives us that this equals b plus a times c. And one more commutative property to say that AC, this is equal to AC plus B. So that one's a lot more complex, but it only uses the left side to the right side, whereas the other method went from the right side to the left side. So that's why there was some disagreement, because at least when I took the class, we can go from one side to the other, but that may not always.
Could you not just start with the AC plus B since they're equal and end up with the A plus B times B plus C?
Yeah, you can do that as well. Yeah, and because of all of that works because of the commutative property, because we know that these equivalencies apply either way, because we know that commutative applies to Boolean algebra. Okay. So let's go ahead and move on. Oh, one more question.
Yeah. So are we gonna be asked at some point to like just solve it just from like one side instead of like us working on both sides to like get to the same point? Or
can you clarify, like in this problem, what would that look like?
I'm not sure in this problem. There's like on last homework there was like a couple of problems where you can like kind of work on both sides, like kind of like applying commutative and distributive but like in both sides to like get to the same point. I'm not sure if that's
Right.
possible.
I think that as far as I know about Boolean algebra, I think that would work. I don't know if it would be the easiest way. I think it would end up possibly getting a little bit confusing with all the variables, but I think it's definitely allowed. I can't say for sure if we would ever like specify that on a quiz, but I think that for the most part, we usually will not be too picky about how you solve these. It'll probably just be a problem statement like this, where we just say use the properties to prove.
Okay, thank you.
All right, so we only have a few minutes to be working on these quiz problems. So instead of having you work on these, we're just going to get right into them, since probably you already tried them on your quiz as well. So let's go over our proof by cases. We want to show that 3 divides n cubed minus n. So I think probably where a lot of people struggled with this is just figuring out which cases to use, because it's not immediately obvious. When I first tried this problem, I started with even and odd, and pretty quickly if you try using it with even numbers, it's not very easy to solve it. I don't even know if it's possible. So what is another version of cases that we could use rather than even and odd that would still be a partition?
Remainder of 3.
So let's start with remainder equals 0 when you divide by 3. So that means n equals 3a, where a is in the set of integers. And let's substitute that back in, minus 3a, and that is going to equal 27 plus, 27a cubed minus 3a. And we can factor here to get 9a cubed minus a. And we can use closure to say that this equals 3k, where k is in the set of integers. All right, our next case is going to be r equals 1. So we have that n equals 3a plus 1, where a is in the set of integers. And again, we can substitute this into n cubed minus n. Okay, and what is this going to come out to? All right, so using when we're to the power of 3 is going to be 27a cubed plus 27a squared plus 9a plus 1 is going to be this section. And then we have to subtract 3a minus 1. So that leaves us with 27a cubed plus 27a squared plus 6a. And again, we can factor out a 3. We get 9a cubed plus 9a squared plus 2a. And we can use closure. All right, there's one more case in here, which is that r is 2. So n equals 3a plus 2. And we can substitute into n cubed minus n. This one is going to give us 27a cubed plus 54a squared plus 12a plus 8. And then we'll subtract 3a minus 2. So that is 27a cubed plus 54a squared plus 9a plus 6. And again, we can do factoring. Let's see. 54 divided by 3. My goodness, I'm having struggles today. 54 divided by 3 is 18. 18a squared plus 3a plus 2. And that gives us 3k again. All right, sorry, we are a little bit over time because we got started a couple minutes late. Are there any questions on how we did this proof? Okay, awesome. Then there are a couple more quiz problems that we wanted to go over, but we will do them in next week's discussion instead. And you are all free to go, but we'll hang around for a minute if you have any questions.
Thank you.
Thanks.